Okay.
You know what I mean, like you
It's
can.
on TAD, and I think everybody else.
He said he was gonna like go out for milk and he never came back.
Seems like NASA is not military.
Okay, today, again, we're just having a little bit of a tour of maybe the waiting room of the sausage factory, as it were. Just this approach using events to model. We've already captured things that move around, seen some different rules, and now we're kind of looking at, again, an approach to how we can model these detection and undetection events. And what we've had so far is the idea that outside of the maximum range, then there's nothing to do. There are no events that would necessarily be happening until a target enters that maximum range, and then there's a potential for detection. Now, as I hope you can imagine, for a given equation of motion, there's really only one formula, as it were, for figuring out when that enter and exit range occur. Actually, for a given equation of motion and a given sensor footprint, again, we've just been looking at the simplest one, but the same concepts apply even for more complicated situations. You know, again, we're just looking at the simplest ones. But once you're sort of in range, then the rules by which you detect the target in general are a function of a whole lot of things, including the, when you get into radar, you get into radar cross sections and radar range equations and things like that. And with other sensors, sonars and even visual sensors and things like that, you get into, again, a lot of complicated things. And all of these can be played out with the same methodology, only we're just using the simplest one, which is we're not capturing things like the environment, we're not looking at things like background noise or the contrast, like when you're looking at visual detections, you have basically the contrast between the signal from the target and the background, stuff like that. So just kind of looking at the simplest thing. And the thing is that when there are a whole host of these things. And so as a first cut, we can abstract those by simply modeling the time from when a potential detection can occur until when it actually does occur. And so for that, even for the same equation of motion and the same sensor footprint, you're going to have there are a lot of different possibilities. So you want a framework in which that's something that you can fairly do. And so this is one way to do it. Obviously not the only way. There's always one more. What is it? I don't know if anybody programs in Perl anymore, but they had one of their phrases, which is kind of an interesting one, which is abbreviated to Tim Toady, which is there's more than one way to do it. So, okay, so this is a way. And in terms of mapping the event graphs to classes and kind of using this kind of quasi-object-oriented idea with the event graphs, it turns out that the same principles apply, namely that it is useful to take the common attributes and behaviors of a given related set of classes and put them in a single base class, which is ideally abstract. So, so from an event graph standpoint and also from a class standpoint, that's what I'm calling the simplest abstract sensor. Again, these examples that I'm showing here are really just purely for classroom type of stuff. And as we'll see, they leave a little bit to be desired when you're trying to do a more complicated scenario. And then that's basically what I've made you do, is kind of take the next step beyond what we're doing here. So the idea is that, again, once you enter the range, then how do you detect it? Well, the simplest one is it's called a cookie cutter. The idea is that you just get detected immediately. And how realistic is that? In some situations, it's not as bad as you might think. For many of the models in the literature that try to do similar types of things, they like the cookie cutter sensor because it's very analytically tractable. But then, if you notice that there's always some kind of reaction time. And so the simplest way to model reaction time is just with some constant. So the reaction time of the sensor, like once it starts receiving signals back from the target, then it's going to take a little bit of time to process it and decide that there's something there. The simplest one is that constant. And then the next simplest one is what I'm calling the constant rate. And the motivation for that actually comes from a time step or glimpse-like approach, where with every glimpse you're detecting with a fixed probability. And so, as we kind of talked about last time a little bit, that leads to a geometric number of glimpses until you detect it. And then in a continuous situation, the geometric distribution is actually the discrete version of the exponential distribution. And so if we simply have a mean time to detect and we apply an exponential random variable, then that gives statistically the same result as, as this glimpse idea. And it's typically more efficient. I mean, in other words, if I need to take, say, 100 glimpses, as opposed to simply generating one random variable, I mean, that's generally a lot slower. So the idea is that in order to figure out when the range gets entered and exited is this referee concept. And then in order to schedule the actual detection and undetection events, that's actually where the time to detect is modeled in these things called mediators. Now, and as we'll see, in the simplest version, because there isn't information in the events about which movers are running around, in order to make this work, we need to have one referee per mover, basically. And of course, that it turns out that if there were just a little bit more information, which is what you're doing and what I asked you to do, then all you need is just one referee. So that's a difference between what we're doing here and the other. So, but the mediator is actually where the model for detection occurs, as we will see. So the idea is that the sensor objects, they have these detection and undetection events. Again, everything in discrete event is about events. And the idea is that each sensor is going to maintain a list of the detected targets. And now, since the sensors could move around, and we'll see a little demo of that later, the idea is instead, again, the principle of laziness says rather than redoing something that we've already done with our mover objects, we can either subclass it, as it were, or we can delegate it. And inheritance has its uses, and when object-oriented first came out, they kind of went a little crazy with it, to the point where it just got overused. That's my opinion. It has its uses. And this is one of them. One of the uses is to have an abstract base class and then have subclasses which have the same common implementation in the base class, but then customize it. But for something like this, actually, I think a delegation pattern is a little more, I think it's just a little bit better. Unfortunately, and there are languages that actually directly implement the ability to do that. Java doesn't, so it would be nice if Java did. In other words, it would be nice if I had the ability in a class to say, okay, I have these methods, and I have signed on to these methods by implementing this interface, but I don't want to implement them. I want to simply say, these methods are going to be handled by this guy. So I'm as stupid.
Does Java not have some sort of mechanism like a function pointer essentially?
They don't have function pointers, they have method objects. But, which is, but it, I mean, what I'm saying is that the language itself have a delegation mechanism, which Java doesn't. There are languages that do. It's not a common thing, but, Python doesn't have that, but anyway, so the idea, again, we're using this listening thing, again, because, again, just in discrete events are the thing. So our referee object listens to a mover, and it listens to a sensor, and then decides when the enter and exit range events occur. And the reason why you need some third party about that is that you don't want to have the sensor deciding when it can see a target before it sees it, and you don't want the target to be saying, that sensor, that guy that's around the corner, when is he going to see you? I mean, so this third party, the referee, simply says, okay, I'm listening to this guy, and I'm going to tell the sensor when, eventually going to have some events that are going to lead to the sensor detecting it. And that's where the mediator comes in. So we have a mediator who's listening to the referee, and that's what's going to schedule the detections and the undetections on the sensors of a given type. So our abstract sensor, the abstract class or event graph that has all of the methods and parameters. So its parameters, it's going to have a mover, that's its delegate for how it either moves around or where it is. It has a maximum range, okay, so that's how we're going to decide its footprint, and we're going to say all the footprints are going to be circular. Again, all of that can be generalized, and its one state variable is just a set of contacts, which will contain the things that are detected. And I'd say that we're going to delegate some implicit states. So, for example, just as the implicit state for the mover was based on the equation of motion and its discrete event states, likewise, the current location and velocity of the sensor are going to be gotten from the mover. So the event graph looks like this, and it's fairly simple. So here's its delegated mover. And so just a way to do first we have our states which change, our events which change our state variable, and they are simply detection, which adds the argument to the contacts, and the undetection, which adds removes the argument from the contacts. Then, and this is because because the referee needs to know when the movement state of both sensors and targets have changed, then we need to have an event that signals that. And the way that that's done here, and again, this is a way to do it, is we're going to listen to our delegated mover, and when our delegated mover has a start move event, we're going to schedule what I'm going to call start sensor move. And likewise, when the delegated mover ends its move, we're going to schedule an end sensor move. And these events are what the referee is going to be listening to. And again, this is in the implementation, this is abstract. And so to implement the specific ones, say for the cookie cutter, we simply have to subclass it and make it a concrete class. We have no additional parameters because Basically, as soon as you step inside the cookie, we see you. As soon as you step outside, we don't see you. The constant time, though, I mean, it doesn't add any, all of these subclasses are very, very small. They will typically only add parameters. And that's so that the same mediator class for a given type of sensor can handle whatever it is. We'll see that with the mediators. So the idea is that we have a fixed constant time between the enter, range, and detection events, and so we simply will add a parameter, we'll call it time to detect, and no additional events. And then for the constant rate now, we want a random time between the enter, range, and detection. We're not going to, again, not have any additional events. But the idea here is that, and this is something we're going to learn about in our next module. So after today, we're going to actually turn the page after today, and we're going to start taking a brief tour of the random variate sausage factory. So that's starting tomorrow. And when we do that, we're going to notice that for the exponential distribution, if I have an exponential random variable with a mean of 1, and I multiply it by some other positive value, then that turns out to also have an exponential distribution with that same parameter as its mean. This is, by the way, not true for every random variable. It's true for some of them, but not all of them. For the exponential, it happens to work, so that just makes the implementation a little bit nicer. So the idea is that random time is going to be an exponential random variable, which is going to be between the enter range and the detection time. So our referee is the one responsible for scheduling the enter and exit range events. And now for the simplest version, our parameters, we have one mover and one sensor. And it's going to listen to the start move and end move events from the mover, the sensor start move and sensor end move events from the sensor. And then it's going to use that quadratic equation roots to schedule either the enter range, the exit range, or do nothing. And the event graph, I mean, it looks fairly complicated, but it is actually quite simple because just in terms of creating an event that I call enter exit times, that's where all the calculations going to happen. The alternative is to kind of have essentially the same code in all of the different events. So basically wrap it up in this one. And then because the movers can kind of shift just because so for example, so if this is our sensor and our target is kind of starts moving like this, we're going to schedule an enter range here based upon the quadratic formula. But then if the target decides to, say, make a right turn, now it's going to miss, and we need to cancel this event here. That's what these canceled ranges are, canceled events are here. So basically, the enter range and exit range are going to have as their arguments the mover and the target. The target, that's the mover, and the sensor that it's for. And that's kind of where we got to. Except now let's look at the mediator. So the mediator is going to listen to the referee for its enter and exit range events, schedule the detection and undetection events for a sensor of a given type. So the cookie cutter simply says, okay, we're going to listen to the enter and exit range events from the referee. The arguments are going to be the mover, target, and the sensor that the sensor is on. And then for reasons that actually have nothing to do with the simplest one, what we want to do here, and then this is just one last little tweak on on how the event scheduling works, is that we actually schedule the wait delay on the sensor itself. In other words, and that's kind of what this notation is. We're not going to delve too deeply into that, but you'll see it in the implementation. So enter range is going to schedule a detection, and exit range is going to schedule an undetection, all with 0 time. Now once you start having time delays between those, then a few extra little nuggets kind of come up. So for example, in the constant time, there's going to be a delay between when we enter range and when we detect. And that's going to be based upon this parameter in the sensor, the time to detect. And because that's a parameter of the sensor, then we don't have to have a separate class for each possible value of the time to detect. So when we enter the range, the difference here is that notice that there is a delay, and that delay is the time, the time to detect parameter on the sensor. And then we pass the target, the mover, as the argument, and so that gets past the detection event of the sensor. Now here's the issue. Oops. Okay, so supposing at some point, where are you? Come on. Okay, so supposing at some point, actually I need a bigger one. Okay, so let's say here we are. We have an enter range here. What often happens is that our detection event, say, gets scheduled here, and then we're inside the range, and we get to we get the detection, and then when we actually exit the range, then that's where our undetection happens. But what if we're in this situation? So here we've entered the range, and we're kind of heading this way, but based on how fast we're going or how much of the sensor's footprint we have decided we're covering, our detection event may be out here. And so what happens is, so if we don't do anything, so here we enter here, we've scheduled our detection here. Now the exit range happens before the detection. So what should happen? Well, here, we can't detect the target out here because we're outside the range. You know, again, in a more complicated scenario, obviously you would have, you know, like if we're like an observer, for example, and we see, let's say we see a vehicle kind of going this way and we're still kind of looking around, and we look at it a little time later, we're not just going to be looking randomly, we're going to be mentally doing some kind of dead reckoning and say, okay, he was here, he's kind of going like this, he ought to be around here. So, and we, you know, as I'm sure you're all aware, we can apply dead reckoning even if we can't see the thing, except the problem there is that we don't know if the target has continued in the same motion that it has. And once we don't see it, it could have been doing something else entirely. So we can't say for sure where the heck it is. So really what we need to do is when the exit range happens, before the detection, we need to cancel that detection. Otherwise we're having the sensor see a target for sure when it has no business doing it. So that's what this canceling edge from exit range. So if we have not detected the target yet, that means there's still a detection event on the event list, and so we need to cancel that. And then we'll schedule the undetection. And the constant rate is the same structure, and the only difference is that right here we have our mean time to detect as the parameter for the constant rate, and we compute this by generating an exponential random variable with a mean of 1, multiplying it by the time to detect. That's that's really the simplest way to do it. Alternatively, we could have simply set the mean of the exponential to be this, but it just turns out the implementation works a little bit nicer with this. But we have the same principle. Because there's going to be a delay between the enter and the exit range, we could be in a situation where the detection happens outside, that is after we've left, and we need to cancel it as we've done here. Okay, so now actually do anything. Well, let's take a look. Okay, so here's the abstract sensor. Again, it's a SIM entity base. It has two parameters, the maximum range and the mover. And then its state variable is a set of contacts. And this is, the implementation is, so in this particular case, we need to make sure that the contacts are actually instantiated. For some reason, I don't know why I did, it made it a linked hash set rather than a hash set. By making it a linked hash set, that kind of makes it a little bit of a first in, first out type of thing. Which type you have is in a more complicated situation, you might have slightly different rules for which ones you want to kind of keep at the top, but that's kind of, so yeah, our initially we don't see anything, and so our run event is simply going to fire that property change. So here's the detection event, and so this simplest abstract sensor is going to be able to detect these simplest mover guys, and so we will add it to the contacts in the usual way. And then just for maybe more debugging purposes than anything else, also have a kind of an implicit state, which is, this is the target that I've detected. Just as again, it is not essential to anything, but is helpful for debugging purposes. And likewise, the undetection. We simply remove it, and then I say, oh, by the way, I've undetected this guy. Okay, so here's, remember that we are listening to a simplest mover, and so they will schedule a start move event. So this is how, if we're listening for that, we're going to schedule a sensor start move event when we hear that. And likewise for the end move, we'll schedule a sensor end move event. And then our current location is simply our mover's current location. And likewise, its velocity is, again, so I was stupid. And then, of course, when we have, because Java does not have things like non-negative variables, we have to worry about, just because I make this a double, it means that somebody, we could accidentally give it a negative value. And then the question is, what if I have a sensor that has a range of 0? Well, what kind of sensor is that? I mean, that's pretty useless. So if you try to do that, and there's nothing in Java that will prevent us, but we can say, okay, if you try to do this, then I'm going to give you an illegal argument. The other thing, so here, when I'm going to set my mover, I'm going to actually add myself as a sim event listener. That just makes sure that it happens instead of relying on someone else to do it. My contacts are going to be a copy. Now here's where, again, for debugging purposes, it turns out that what I'm interested in for these are actually things like its state. Its movement state. So I want to make sure that my sensor is actually kind of where it is, and so I'm going to override the toString and give it the location and the velocity. And I picked out the coordinates because I could have just done the toString of 0.2D has a bunch of other, it says 0.2D blah blah blah, and that's just a bit noisy for me. And I still want to see the parameters though. And so I create another param string, and what that does is that returns the super toString, which has all the parameters in it. So that's the, okay, so let's look at the cookie cutter sensor basically, all it does is it just has constructors, because it extends our simplest abstract sensor. But the key thing here is our mediator. So our mediator is going to listen to the enter range events, which is going to hear from the referee, and then simply schedule a detection at times, with 0 delay on the target. And it would hears an exit range from the referee, it'll schedule an undetection from the target. Now, probably the most complicated things of these are the referees. For this sort of toy problem, the referee just has one sensor and one target, and that's because in order to keep things simple, those events didn't have an argument that said who is who. So here it listens for a start move, an end move that'll hear that from the mover, then a start sensor move, an end sensor move. Both of those schedule this enter and exit times thing. And so there's a, okay, where was that? When you have a computation, which you're going to be doing again and again, of course, you want to just sort of extract that to a method. So I wrote a method called find intersection, and if you give me a simplest abstract sensor and a target, what it's going to do, this basically goes through, this implements that big equation. And so here you do the determinant, and so if the determinant is negative, then what this is going to do is this is going to return, in fact, so it's going to return an array of roots based on the quadratic formula. And if that array has length 0, that means there are no roots, and so we can do nothing. If it has one root, then that means that there was a negative root, and the one root it returns is the positive one. And if it returns 2 roots, it'll have the smaller one in the 0th place. And so that tells the referee what to do. So I get the roots from that. And so if the length if I have just one root, and I'm just going to double check that it's bigger than 0, then I'm going to schedule an exit range. And if it's equal to 2, then I'm going to schedule an enter range. Okay, so how does all that work? So in this is sort of implementing I'm going to have a target. It's just going to bounce back and forth on the x-axis. So so I'm going to give it a patrol mover manager. And it's going to start at the origin, but it's going to bounce to negative 100 and positive 100. And on its route are going to be one sensor located at minus 30 with a range of 20, and it's a cookie cutter. There's going to be another sensor located at plus 30 that's going to be a constant time sensor, and it has a max range of 30. And then there's going to be yet another one located at 70 that's going to be a constant rate. Okay, so I have all 3, and its mean time to detect is going to be 0.3. So here's how we set the referee. So I have one referee for the first mover, and I have a mediator that's going to be a cookie cutter mediator. And so that's listening here. The second referee is going to be listened to by a constant time mediator. And the third referee is by the constant rate mediator. So we did all 3 of those. And then we're just going to run this in verbose mode for 5 end move events. Okay, so again, want to make sure that, let's see, did I have there? Okay, so this is our target. It's initially located at 0. Here's our cookie cutter. Here's our constant time and our constant rate. So they're all there. And then we see that for every component we have, it's going to have its own run event. And so let's see there. Yeah, the first one is our mover, and we initialize the velocity, and so we spin on the run events, and then notice that the mover run event is going to schedule the next waypoint. The patrol mover manager's run is going to schedule its next waypoint, and that's going to show up at some point. But now our sensors are just basically initializing their contacts to be empty. And then finally, stuff starts happening. So here's the next waypoint, which is our patrol mover manager, and that says go to minus 100 to 100, so check, and our next index is 0. So we have the move to, which in turn schedules the start move event. Now, as we see here, since all 3 of the referees have kind of eyes on this mover, we have 3 enter and exit times, 1 for each of the 3 referees. So for the first one, that was the one at the negative, so that we have an enter range event, which is scheduled in 0.25. We can double check that was the right time. The second one, though, the next 2 sensors are to the right, and we're moving away from it, so there is no enter range event for that. And so that's a check. So this is remember the barking dogs Sherlock Holmes thing where he solved the case and he said, how did you solve it? He says, because of the barking dog. He said, but the dog didn't bark. He said, that's what told him. So, okay, so here's our enter range event for our cookie cutter. It's at time 0.25, and so the detection is scheduled at 0.25. Again, check there. When the exit range occurs, we now have an undetection scheduled, and we see that is happening there. And then we reach the end move, and then we have all these enter-exit times because we've stopped. We're listening for the end move event. We have to spin through those, but nothing is going to happen because the thing is just sitting there. Then we get the move to, and then the start move, and then we do all the enter-exit times again. And now we're going to get an enter range for each of the 3. So you notice we have all 3 enter ranges for the enter. So we have a detection here, we have an exit range, undetection there, etc. And what I want to, let's see, okay, so let's look at the constant time enter range. Where was that? Enter range for the constant time. So that occurs at time 5, and notice the detection is scheduled at 0.5 after that. So that verifies that piece is working. Now let's look at the enter range for the constant rate, and we see that occurs at 5.875, and we see the detection is just some time later, but it's not a fixed one. In other words, the mean was 0.3, but you notice that this is a number different than that. And that was because it was generated randomly. Okay, so that, as you can see, kind of looking at all of the individual events when they occur, the state transitions occurring correctly, that's valuable for verifying that these things are actually working. And that, as you can see, that can be a little bit tedious. So it's, okay, does this thing actually look like anything? And so here's, again, in your graphics class, this is so here's just sort of a simple test of, here I have one mover, and it's being driven by a random mover manager. And so when we kind of look at it, it's just kind of wandering around, and you say, well, what is going on behind the scenes for this? And if we go to verbose mode, we see that this is just doing a start move and an end move. And the difference is, notice that the mover itself is actually the argument on these, and that's what I've asked you to do. And, okay, so that's mildly interesting, but what if we had a bunch of them? So, same thing, only now we have 100 of these guys, and what is going on the event list, it kind of slows down a little bit, but we see that there are 100 end move events, and we have a start move event and a whole bunch of end move events. So the start move and end move events are actually, they're all, the event list is doing exactly what it's been doing since day one, and the events are just happening when they happen to happen. So in terms of things that move around, that's vaguely interesting. Let's see, so now it turns out that you can have slightly different, so here's an example where the mover is constrained to be in this circle, just, so here we have just a bunch of these things, and they just kind of wander around inside that, and they, so they're not allowed to step outside the circle. And again, same idea here. We have the end moves, etc. And we can actually, let's have a bunch of these. So this, I call this the Petri dish. So. Now, as far as the sensors go, here's another interest. One of the things that agent models kind of like, or rather than giving explicit things, they have these sort of vague rules. So here, this is actually the rule here is that the units are actually want to be in the center of, close to the center of gravity of all of the other units. In other words, they compute the center of gravity of all the guys and then try to go there. But if they get too close, then they just sort of pick a random place out and then bounce out. So that kind of looks something like this. And the yellow one is just to kind of keep track of stuff. And what's interesting is that when we have a few of those, then they kind of wander around a lot. But if we have more of them, the more we have, what was interesting about this one is that they don't seem to move quite as, they don't wander around quite as much. And that's because, if you think about it, if you have a whole bunch of people and they're all voting on kind of where to go, then it's like regression to the mean type of thing. And then, you can kind of, let's see, what was this? So what this is if they, instead of getting too nervous if they get right on top of each other, here what this says is they want to stay a certain distance away from each other. So if you notice that there's this kind of empty circle where they're kind of wandering around there. And then this one was kind of interesting, where everybody is trying to go to the center of gravity except this guy. This guy's the green guy is the leader. And so he's just kind of wandering around. And these guys aren't following him, but they're including the leader in the center of gravity calculation. In other words, these guys aren't trying to follow anybody. They're just trying to stay at the same center of gravity as everybody else. And it, you know, so one could argue that this is an emerging behavior type of thing, because we're not saying follow that guy, we're just saying stay in the center of gravity. Okay, just as a final thing. Okay, so in this, this uses the same concepts. I think these are all just cookie cutters, but what this does is it generated a certain number of red guys, a certain number of blue guys. It gave them random ranges. So you see the circles are the ranges of each of these guys is a mover and a sensor. And their ranges are kind of random. The blue guys can detect the red guys can detect the blue guys. And what this little thing up here is this is just logging those. Remember, it was kind of firing those detection events and undetection events. And so that's basically what's happening here. So this is where this blue guy detected this red guy, and here this red guy detected the blue guy. And as you can see, they're all just kind of wandering around according to their own rule, and they're basically, and this is all, again, if we look at the verbose stuff, we see that, okay, that has the referee has something called check mover, but we see start moves, enter ranges, exit ranges. These are all cookie cutters, so the detection events are, basically, so we have enters, exits, all on the event list. And you see it kind of, the reason it kind of slows down is because it's printing to the console just a whole bunch of stuff. So the point here is that we have and in this case, there are actually just two referees. There's one referee to mediate, to handle the interactions between the red sensors and the blue targets, and just a second referee that handles the interactions between the red sensors and the blue targets. So just two referees here, and what they do is they sort of keep a list of all the potential targets and all the potential sensors, and then they just sort of figure all that out. And just one, in this case, one instance of a mediator is all that you need, because we're just doing the cookie cutters for this. So the point here is that we're kind of doing the abstract stuff here, but in a fairly simple manner, you can actually sort of animate these things, and then we can actually sort of inspect each of these guys and sort of see what they're doing, where they are, what their status is, and all that kind of stuff. So in other words, all of this abstract stuff can be turned into, well, in this case, an animation, which shows kind of where things are going. And that's useful because if I want to see what is happening, then looking at it visually is kind of a key point. What this little thing does, and again, this is just it's not like a production level animation type of thing, but what it does is it can animate things which have a location, as we've modeled, and what this does is this actually is like it has a thread. It's a threaded thing, but is also tied to the event list. So what it does is it converts sim time on the event list into sort of clock time, and then that's how these are displayed. Okay, so that's basically what's going on there, and I've asked, and what you're working on is at least the movement portion of this, which is closer to what we're doing here, the next step beyond what we've done in class. But starting tomorrow, we're going to peel back the hood a little bit on what is going on with these random variates. That's something I think there was at least one or two questions earlier in the course that I deferred to this, and now I'm going to come back to that. So we're going to look at the random variate sausage factory a little bit, and we will start doing that tomorrow.